Hello, this is Group 20, and this is how to make an advanced breadboard. Here's our team. First, there's Christian Gutierrez, who's a computer engineer. Next, Amar Mubaraz, our electrical engineer. And finally me, Sheridan Sloan, computer engineer.
So what are our motivations for this project as to why we did it? Well, the main motivation in general is to teach people how to convert their schematics to actual breadboards so that they're able to make circuits. Now, in order to do that, we also thought it was a good idea to help students learn how to find and detect short or open circuits, which we find in our experiences in the lab to be something that a lot of people do, whether they're beginners or even advanced. Oftentimes they might make a mistake and put a component where they should not be. Additionally, this also happens simply because they may or may not know where to put it in general. If they don't know what node is which or how to understand how each node interacts with each other, we thought that this was a good way to fix that so that there's a more clear understanding of nodes.
The main goal of the project is to add features to a breadboard that will help a user avoid mistakes. This goal can be broken down to a few objectives. There will be a schematic building tool similar to Multisim, which will then tell the user how to connect the circuit onto a breadboard. To help the user avoid making mistakes with the placement, there will be LEDs that light up which node on the breadboard should be occupied. There will also be open and short circuit detection. The device will also be battery powered, which leads to the last objective of portability and accessibility. A few stretch goals were added as well. The first is achieved as we originally were only going to work with 3 nodes and will now have 9. Another goal would have been to make the software work where it could create a
As you can see, our motivations directly reflect our engineering specifications. As on our GUI, we can confirm that we have less than 10 seconds every time it interacts with the ESP to get our sensor data. Additionally, the activation of the LEDs on the breadboard are more than 95% accuracy on correction, and that is the same for the open and short detection.
Here is an overview of what the process will look like. First, the user will build their circuit on the GUI. Then the algorithm takes that circuit and returns a screen with how the user should place those components on the board. Third, the LEDs on the breadboard will illuminate which node should be occupied. Next, the user will have the chance to place the components on the board. And finally, the software will check for any open or short circuits.
So this is our hardware overview. What we'll be looking at is a flowchart of how all the hardware components are connected and cooperate with one another. We'll first start off with the battery pack, which is a true AAA batteries that should output a range between 0.9 volts to 3 volts. This will be used to go into as well as power the voltage regulator, which is a boost pass-through voltage regulator, which means that if the voltage is between the range of 0.9 to 3 volts, it will boost the output to 3.3 volts. And if it exceeds 3 volts, which in some cases the AAA batteries may go up to 3.2, 3.3 volts, it will act as a pass-through and will allow that voltage to be the voltage output. So the voltage regulator will power 2 main components as well as just putting power through 2 buttons. The main components are the voltage and current sensor. It will be used to power that, and then the user's power supply will act as the the sensing between the voltage power supply and the user circuit, which are both connected through the sensor. So the other main component is the ESP32 that will be powered by the voltage regulator as well as the battery pack. From here, the ESP32 will power the LEDs and turn them on corresponding to whatever node is on our GUI. The 3.3 volts will also be going to our buttons. From there, we'll be able to put our ESP32 into boot mode or reset the code if there's any bugs or glitches while it's running. The ESP32 will be communicating with the voltage and current sensor to get that data and communicate that with the Raspberry Pi, which is connected to and powered by the battery pack of the Raspberry Pi, and it'll connect to the LCD screen to kind of show us what's going on with the GUI. And the ESP32 will be communicating with the Raspberry Pi because of the GUI, And that is exactly how our hardware is connected with each other. For the voltage and current sensor, we had to choose between three components that is all manufactured by Texas Instrument. The three components are the INA 219, INA 260, and INA 2333. Of the three, the INA 219 is the cheapest, as well as an operating voltage between 3 to 5.5 volts, while the other ones have 2.7 to 5.5, which are in range with the other two components that we're using in our PCB, so that doesn't require any additional voltage regulators. So sensing voltage for the INA 219 is 0 to 26, while the others are 0 to 36. This is a little bit of an overkill for the intended circuits that the user is intending to build for our design. So we decided to just stick with the INA 219 to save money. As well as the accuracy being 0.5% maximum error, which is the highest amongst the three. That 0.5 isn't really making a big difference for the measurements that we're making, since these measurements are off by plus or minus 2 millivolts or plus or minus 2 milliamps in some cases. The interface that they're all three will be using is the I2C, which seemed to be a very good way of communicating with the ESP32, and they all have an ADC, which, looking at all of these different categories, we discovered that the INA 219 is the most ideal for the scope of this project.
Once the sensor was placed on the PCB, we were able to test its accuracy. It was important to determine the resolution of the sensor so that an open or short circuit could be rightfully determined. In this test, a sample circuit was created and the current and voltage were measured using the sensor and fluke meter. The sensor is not as precise as the fluke meter, so the latter was used as a base for measurement. When the current approached 1 milliamps, the percent error of the sensor increased to almost 35%. Values around 2 milliamps and above maintain percent errors below 5%. It is for this reasoning that the lowest current that will not be considered an open circuit is 2 milliamps.
So the variable power supplies, we had three to choose between, which are all very common for laboratories and schools and for home use. The first one is the Alenco, second is the CORAD, and the third being the Keyprim. Of the three, the Keyprim is the most expensive one, but it offers a lot more features that the user will find to be very useful for their power supply. It outputs 0 to 30 volts, which is a little bit of an overkill for the intended circuits, but just in case that the user wants to go through this, they can do that. For the output current, we have a 0 to 10 amps, which again may be a little bit too much for the intended circuits, but this is always a good option, especially with this programmable power supply. We're able to limit the current in order to save anything with short circuit. For all three of these, they do offer short circuit safety, which is kind of very vital since we don't want to damage the user's circuit, which is really good. And the Keyprim has a digital display, making it easier for the user to kind of see in real time what's happening, what's the power supply outputting in terms of voltage and current. So for the battery pack, we decided to look into three different kinds of battery types that are very common. We decided to look into alkaline, lithium ion, and zinc carbon. Of the three, alkaline has a range between 850 and 1200 milliamp hour depending on the brand, but we can see that lithium ion and zinc carbon have a custom constant 1150 or 1100 milliamp hour. For the self-discharge, we saw that the alkaline has a 2 to 3% per year, and the lithium ion has 1 to 2% per month, zinc carbon having 0.32 per month. So we can say that alkaline in this case can save or last a little bit longer. For the shelf life, 5 to 10 years. So we're not really looking into shelf life with the use of the advanced breadboard, but we can see here that the alkaline and the lithium ion last a lot longer when it comes to shelf life. What was really important was the temperature performance, and we can see that the alkaline and the lithium ion were very close to how they operate within the temperature performance. But then we came down and saw that the alkaline, not only is it the most ideal battery type, but we saw that it was very common in terms of household use. And we want to be able to give the user the accessibility to be able to switch and replace the batteries whenever they lose charge or whenever it's time to change or if there's any damages to the batteries. So we decided for those reasons we would go with alkaline batteries. For the brands of the battery for the alkaline, we decided to look into 3 Duracell AAA batteries, EN91F3, and the Zeus AA. These are common alkaline batteries that are ideal for the use of the advanced breadboard. We can see of the 3, the Zeus AA is a little bit more expensive, but we can see that for the quantities needed to power the advanced breadboard, it requires 3 batteries, while the Duracell AAA requires 2, and the EN91F3 is just 1 battery. The reason why we needed these quantities is for the voltage output. We can see that the Duracell AAA batteries outputs 3 volts, while the others output 4.5. As for the capacity, we can kind of see that using 2 batteries gives us a capacity of 2300 milliamp hour. And since the advanced breadboard requires less than 500 milliamps, we saw that this is the most ideal situation, as well as the common use of Duracell AAA batteries and how common they are within households gave it the advantage compared to the other 2 batteries. And we decided, thanks to the output voltage of 3 volts, as well as the input voltage of 3 volts for our voltage regulator, and the ease of design changes with these batteries, the Duracell AAA batteries was the most ideal. So for the voltage regulators, we have 3 voltage regulators that we had to look at: the TPS 61023, the TPS 613321, and the TPS 82150. Of the 3, the TPS 61023 had the medium cost range of $1.18, while the 613321 had a 58 cents, which was the least expensive. We also want to look at the frequency switching, and because these are boost pass-through, the frequency switching actually mattered in this case, and we saw that the TPS 61023 had a really good frequency switch. For the input voltage, we saw that the TPS required 0.5 to 5.5 volts, while the 613321 had 0.9 to 5.5, and the other one had 3 volts to 17 volts. Because we're using batteries, the voltage will drop as the batteries are being used, so we needed to use one that had 0.5 to 5.5 volts. And you can see that the output voltage ranges between 2.2 to 5.5, but we decided to stick to just 3.3, as well as the maximum output current being 3 amps. This was really good just in case that, the amps of what we're using starts to increase. So by looking at these, we saw that the TPS 61023 happened to be the most ideal. For the LEDs, we had a choice between 3 different ones. The first one is the WP7113, the second is the Shenzhen 5mm diode lights, and the third is the LTST C191. Between the 3, we can see that the Shenzhen is the most expensive in this case, and that is because we're getting the price of an entire pack of 100 LEDs, while the other ones are just the cost of 1 LED. So we can see that through that logic that the Shenzhen does have the most worth value. For the forward voltage, we can see that the WP7113 has a 1.95 volts, while the Shenzhen does range between 1.2 volts to 2.3. That's because the Shenzhen comes in a pack of 10 different LED lights, so each of them has a forward voltage that is a little bit different than the others. For the LTST C191, you can see that there's a forward voltage of 2 volts. And as for the viewing angle, the 30-degree viewing angle of both the WP7113 and Shenzhen is very similar because they're almost exactly the same in terms of look. As for the LTST, it's a very different LED, which is why it has a 130-degree viewing angle. For the luminous intensity, we had to carefully consider this because we want the user to be able to see this from a very far range, because this can be used as a learning tool. So being able to see it from afar is very helpful, which is why the WP7113 and the Shenzhen had a high luminous intensity, and why we considered getting either one of these different ones. But we ultimately decided to go with the Shenzhen 5mm diode lights because it comes in various different colors. We can use each color to represent a node in the advanced breadboard, which makes it very easy for the user to differentiate between these different nodes.
For design, there's an embedded system made up of an ESP32 room chip on the PCB and a Raspberry Pi 4B. Both devices will be wired using the USB-A to RS-232 cable. This way, the Raspberry Pi can direct the ESP32 to turn on certain LEDs or grab current and voltage information when required. The Raspberry Pi required its own power supply, and since they required close to the full 5 volts and 3 amps, a cable had to be specially made. This was a 14-gauge wire soldered to a Type A connector and a Type C connector. This could be plugged into the wall and to receive the full power it needs, avoiding a low voltage warning.
For this project, we knew we needed something great to be able to handle the software in the GUI. And so for our main processor, we thought of a lot of things, but we ended up coming to the Raspberry Pi 4B. And this is mainly because we saw that the Pi has not only equal documentation to popular microcontrollers such as the ESP32, but we saw that the Pi is simply much stronger. On its own, it's its own computer. And although we're not 100% sure at the time of choosing this whether it is too much, at the end of the day, we found that it was a perfect amount of computational power and storage in order to complete this project.
Choice for the microcontroller was a simple one. There was no need for anything that had high processing power or large amounts of storage, since the Pi handles the heavier load of the software. The ESP32 was chosen over the MSP430 because it has native libraries for the sensor that was chosen. There are also plenty of example programs and tutorials for learning how to use the ESP32 quickly.
So for our PCB, we can see that there are two images for this slide. The first one is our most updated and organized schematic of how all the components are working together. This picture has broken down each component into a kind of a box. You can see in the top left-hand most box, that is the sensor, while the one to the right of it is how the LEDs are connected, while the one to the right of that are how the buttons are routed, while the one to the right of that are the header pins for the sensor. And then when we look down, we can see that there's in the bottom left-hand corner, the voltage regulator and the schematic for that and how it works and where it's outputting. And then to the right of that, the ESP32 and how everything is connected to the ESP32. In the bottom of this image, we can see that this is our most recent PCB iteration. You can see that all the components are already soldered onto this PCB and how everything is connected. You can see that the vias are spaced out and all over the PCB, connecting the top two ground planes. And then in the bottom left-hand side of this PCB is where the sensor is. On top of that section is where the voltage regulator is. You can see the the LED lights are in the middle of the PCB. And in the top right-hand side, you can see the ESP32, and underneath that are the buttons in order to route and boot and reset the code for the ESP32.
Here is a general overview of our software. As you can see, for the software, the top portion is blue, and that is mainly what I will be talking about. The teal and green will be later discussed in the slides. But for the blue portion, we could split this into pretty much three sections, that being the GUI, the translation, and the circuit graph. In simple terms, the GUI, as the name suggests, graphical user interface, this holds everything that the user can actually see. And so when a user places a component down and they can see the actual component on the screen, that is part of the GUI. And so in short, it consists of everything the user can see, ranging from the circuits that they're making to the newly translated circuit or the data that they're asking for from the sensor. Now the translation is more in terms of the algorithm, and it allows the code to correctly identify the connections the user made and convert that into a new translated circuit that the user can put together on the physical breadboard. It also it also calls for the connections and the sensor data that the user might ask for. And lastly, we have the circuit graph, which is pretty much something that's always running in the background. Now the circuit graph is responsible for keeping track of all the connections that the user makes, as well as connecting those connections to previous connections, or just doing anything with component logic in terms of maybe where it has been put down, to the value that component has, to the label that the component component is given from the user. This is a software subsystem overview, and as you can see, pretty much that is hosted on our monitor has the program and obviously the GUI where the users can interact with. And here they can make their circuit, or they can collect or use components to connect to each other, as well as they're also given the option to translate their circuit with the translate button, which calls the algorithm in the background to make a newly translated circuit to make in real life on the breadboard. Here's a picture of how our GUI actually looks like. As you can see, it consists of many basic components as well as basic tools or quality of life features, such as toggling the values, which allows you to get rid of ohms, for example, if you're using resistors. And so while the ohms are still on that resistor, you just won't see it, so that there's a much clearer view of what your circuit looks like. As well, resetting the entire circuit if you want to make a brand new one, or resetting LEDs to simply turn them off on the physical breadboard. Here's a deeper look into how we made the GUI itself. Now we use a Python library called tkinter. Now one of the reasons we use it is because it's not very complex. It's easy for users to use, and so that would allow us to focus more on functionality before aesthetics. And so tkinter is not only easy, but it is native to Python. And so what that means is that we did not need to have any extra or included downloading just to be able to use this library. And so overall, we chose tkinter because of its simplicity, and we knew that it had all the features we could possibly need for this sort of project. So this is how the translational algorithm works. It's actually quite simple. Thanks to the connections that the circuit graph has been collecting from the user circuit, we're able to send those over to the translational algorithm and have the algorithm filter them to make sure that no connections seem irrelevant and to make sure that the connections make sense. Once this newly filtered connections array has been created, it finds the amount of nodes that have been used in that connection list and then randomly turns on those amount of nodes. Once those nodes are turned on, we display those connections to the user so that the user knows what connections they have to make and what nodes they can use to be able to make the breadboard circuit. So here's a simple user case diagram. Now, here are all the actions that the user can make. In terms of creating the circuit, that consists of selecting components, connecting components, and adjusting component values. And if they are physically making the circuit on the breadboard, that is another action we allow because we have our own physical breadboard. On top of that, they're able to view sensor data by requesting for it in the translate screen, as well as getting to that translate screen and seeing their newly translated circuit by pressing the translate button that is found on the main circuit simulator GUI. Here's a simple class diagram which shows the relationships between all the classes and how they work. As you can see, circuit simulator is kind of the main thing, as it's able to call the logic for the circuit graph while also calling the translation to show to the user on the translate screen. Additionally, as you can see on the right, we have components, which consist of all the components the user could put, including the wire, which is a little bit different because the wire is used to dictate what components connect to what.
Raspberry Pi and ESP32 use serial communication to ensure fast transmission and reliability. Here I included a flowchart of how the exchange of information would look. It was important to only send messages when the other was expecting it. Acknowledgements were used to ensure messages were properly being sent. This was done using loops that would scan the serial for input. It would then check the contents of the input for specific commands. These commands, such as the word matrix or get sensor data, would jump out of the loop and perform the necessary actions. But when the Raspberry Pi sent string messages, they needed to be byte encoded using UTF-8 to ensure the messages can be properly received by the ESP32.
Now, throughout the design, we went through a lot of different iterations. Here's the first one, which has drag and drop, and it has a picture of how the components would look like on an actual schematic. But the UI did not seem too intuitive, and the connections was difficult to put together. Here's our picture of our second design. As you can see, it's very similar to our final. It has a lot of great pros, but at the end of the day, we didn't end up going with it because keeping track of the connections was proven to be difficult once again, as putting the components together were more like pictures rather than keeping track of an actual coordinate system. Here's our final design where we kept track of components correctly by using a coordinate system, and it has a lot of utility features here, such as resetting and a lot of the things I mentioned before, as well as a very simple UI and a simple translation method. And so overall everything seems simple. The only positive con could be that instead of having this program run on one screen, it would open up another screen.
Here we have an itemized list for our budget. A lot of what was purchased was used for testing or prototyping purposes. On the first line with PCB parts, that included 2 sets of orders for PCBs, including all the parts that must go on it as well. We were able to split up this project based on our strengths. Amar took the lead on the hardware side, including the PCB and power supply. Christian focused on the software for the Raspberry Pi, including the algorithm and GUI. I focused on the integration of software on hardware, including ESP32 programming. There was a lot of overlap between us, which helps that no one had to do anything alone. Thank you for watching our presentation and having interest in our project. We hope to impress you at the live demo.